Okay, so in this class I want to talk a little bit about triangle congruence. And congruence just means things being identical. So two triangles are said to be congruent if they're identical in every way. So remember, every triangle has 6 parts. It has 3 sides and 3 angles. They're called the 6 parts of the triangle. And two triangles are congruent if and only if each part of one triangle is congruent to its corresponding part in the second triangle. So if we know the triangle ABC is congruent, there's our symbol for congruent, 3 dashes for a little bit like an equal sign but with 3 dashes. If triangle ABC is congruent to triangle XYZ, then, well, there's a number of things. First of all, the angle A would have to equal to the angle X. Capital letters for vertices and angles. The angle B would have to equal to the angle Y. And the angle C would have to equal to the angle Z in measure. Another way of saying that is the angles are congruent. Each of those angles would have to be identical. Also, the length of the side AB would have to be equal in length to the side XY in the second triangle. And the distance from A to C would have to be equal to the distance from X to Z. And the distance from B to C would have to equal to the distance from Y to Z in my two triangles. Okay, so, triangles ABC and triangle XYZ. Okay, looks something like that. So each part from this triangle would have to be exactly identical to its corresponding part in the other triangle. That's what we mean. To prove triangle congruence, we use one of the following 4 axioms. An axiom is a statement that we assume to be true without any proof required. It's usually something that's really obvious. A theorem is a statement that has been proven using some kind of mathematical proof. There's the side-side-side congruence axiom, the side-angle-side congruence axiom, the angle-side-angle congruence axiom, and the right-angle hypotenuse leg congruence theorem. Okay, this is also sometimes called the RHS, right-angle hypotenuse side congruence theorem. So there's three axioms and 1 theorem. You're required to know them. So make a note of them, take them down, learn them by heart. I'm going to move on and look at each one being used in turn for a proof. So here I'm given a shape with vertices M, N, O, and P, and I'm asked to prove the triangle PMN is congruent to the triangle NOP. And I'm going to use what's called a 2-column proof. Let me just shrink this down a bit. I'm going to use what's called a 2-column proof. And in a 2-column proof, we obviously have 2 columns. And in the left column, we write what's called a statement. And in the right-hand column, we write what's called a reason. So I'm going to prove that these 2 triangles are congruent, and I'm going to be using the side-side-side congruence axiom. So the first statement I'm going to make is that this side here at the top is equal to this side here in the other one. We're looking at these 2 triangles. And I want to be careful to name these in the right way. So I'm going to say the distance from M to P is equal to the distance from, because I started at M and ended at P, notice M is the corner between that single and double dash. So I'm going to pick this side as the corner between the single and double dash. I'm going to start with O and finish at N. So keeping corresponding parts in the same relative position. This is statement number 1, and statement number 1 will have a reason, and the reason is called reason number 1. And the reason I can say that is because it's given. And I know it's given because of these tick marks here. Statement number 2, well, I'm going to say that this side here, M to N, that line segment is equal to this side here from O to P. So M to N from the first triangle, PMN, is equal in measure to O to P. So they're equal in length. The distance from M to N is equal to the distance from O to P. Notice going from M to N, so starting at this corner point between the two dashes and the one dash, along the single dash down to that side, starting at this corner point between the double and single dash up here. These are called tick marks. So my reason here is also given. How do I know that? Well, we're given here that these two sides are equal. It's given in the question. And then finally, the third thing is I'm going to say this side from the top triangle. Notice this is a common side. So I'm going to say NP from the triangle on the top, the distance from N to P, is equal to. Okay, notice that's the corner at the end of that single tick side. So N to P, so I'm going along the diagonal that way. The corresponding way in the bottom triangle, corner at the end of the single tick side is up there. I'm going to call that side P to N. And so on the top triangle, if I'm calling that line segment NP, well then in the bottom triangle I should be calling it line segment PN, because we're keeping corresponding parts in the same place. And the reason, well, that's not given, but what we have is something called a shared or a common side. So my reason is that this is a common side. So one thing I'm going to just note, and while we're writing this actually as you go along, we've proved that one pair of sides are equal, and another pair of sides are equal, and another pair of sides are equal. And now we're ready to make our conclusion. So statement number 4 will be, therefore, a triangle PMN is congruent to triangle NOP. And notice they're named with the corresponding parts in the same place. So P from the top triangle corresponds to N from the bottom triangle. M from the top triangle corresponds to O from the bottom triangle. N from the top triangle corresponds to P from the bottom triangle. And my reason here is just the side-side-side congruence axiom. That's how we prove two triangles are equal or congruent. We don't need to show all 6 parts. If we can show 3 sides of one triangle are equal in measure to 3 sides of another, then the triangles are congruent. Okay, so that's the side-side-side congruence axiom. Let me look at another example, this time using the side-angle-side congruence axiom, which says if 2 sides and the included angle of one triangle are equal in measure to 2 sides and the included angle of another triangle, then the triangles are congruent. So the included angle, when we talk about 2 sides, the included angle is the one between those 2 sides. So we want to prove the triangles here are congruent. So again, I'm going to 2-column proof, statement, and a reason, and we're proving congruence. So I'm just going to think about the triangles. I'm going to consider the triangles, and I'm going to name these AED as the top triangle, and I'm going to consider the triangle, and I wonder, could you name it in the correct way with its corresponding parts in the same place? So what corresponds to A in the top triangle? Well, that's at the end of the single tick side, that's C. E is a common point there in the 2 triangles, and then D up here at the end of the double tick side, that's going to correspond to B. Okay, so I'm going to name these in the correct way. And I want to prove these 2 things are equal. The first thing I'm going to say is I'm going to look at sides in this triangle and sides in this triangle. My first statement is that the distance from A to E is equal to the distance from C to E. And my reason here, well, it's given. Notice those tick marks, that's given. And then my second statement here is going to be that D to E is equal in measure to B to E. And that's also given. And notice how I'm naming these DE. I didn't say EB, I said B to E because I want the order to be good all the time. And then the last thing I'm going to say is this. And notice I was able to say that statement too because of the tick marks there as well. And then finally, I can say, well, the angle in between those two sides is equal to the angle in between those two sides. So I'm going to say the measure of the angle, I'm going to call it AED in the top triangle, is equal to the measure of the angle. And in the bottom triangle, I'd say CEB. And my reason here, well, that's not given. That's what we call the vertically opposite angles theorem. Okay, which we mentioned before, theorem number 1. Okay, notice we've got two sides, and the included angle, that angle is included. It's actually in between those two sides. That's the key detail. So statement number 4 is my conclusion. Therefore, the triangle AED is congruent to the triangle CEB. Okay, and my reason here is my side angle side congruence axiom. We've shown this side is congruent to this side is congruent to this side, and this angle is congruent to this angle. So we have a pair of sides and the included angle congruent to a pair of sides and the included angle in the other triangle. By the side angle side congruence axiom, those triangles have to be congruent, which means, of course, that that angle would have to equal to that angle. This angle in here would have to equal to this angle in here. Okay? Because corresponding parts of congruent triangles will be congruent too. Looking at my third proof here for triangle congruence is the ASA, the angle side angle congruence axiom, which says if two angles on the included side of one triangle are congruent to two angles on the included side of another triangle, then the triangles are congruent. So we're talking about angles. If I take that angle and that angle, the included side is the side that runs from one angle to the other angle. And again, I'm going to do a 2-column proof, statement, reason, and I'm going to consider the triangles. I'm going to try to name these in the correct way. Really good practice to do that. I'm going to call the top one AED. And if I call the top one AED, I really want to call the bottom one. That's a little error in there. That's a little error. Let me just adjust that in here. That shouldn't say that's congruent. That tick mark is in the wrong place. That should be over here. Okay, so a little adjustment. Apologies. So if I'm saying the top triangle is AED, then I'm calling the bottom triangle BEC. Okay, statement number 1. Well, I'm going to say line segment AE is equal in length to line segment BE. And my reason here is that's given. Okay? I'm also going to say, you know, that this angle here has to be equal to this angle here. So I'm going to say the angle AED, the measure of the angle AED, is equal to the measure of the angle. And the right way to write that now is BEC, not the other way around. Okay? And that is, well, that's my vertically opposite angles theorem. That's what that tells me about. So I have this side congruent to this side, this angle congruent to this angle. So what I need to prove to be able to prove congruence using ASA is that this angle is equal to this. So how can I prove that? Well, the first thing I'm going to note are these little arrows here and here, and they're telling me that the side AD is parallel to the side BC. Okay, and that is given. That's given. How is that given? That's given by the little arrows. Those arrows you see here and here, those arrows are telling me that sides are parallel. Okay, so we have two parallel sides being cut by a transversal. Notice that's two parallel lines. That's parallel to that. Being cut by a transversal. That big diagonal there is a transversal. And we know if that's true, then the pairs of alternate interior angles are equal. So that angle is equal to that. So I'm going to say the measure of the angle. Notice I can call this angle A here because it's the only angle happening there. I can't call this angle E because there's four different angles with E as the vertex here. But the angle A, there's only one angle with A as the vertex. So I'm going to say the angle A is equal in measure to the angle B. Okay, the angle at A is equal in measure to the angle B. And the reason for that is that's the alternate interior angles theorem. Okay, and then what we have, note, we have a side, we have an angle, we have another angle, but what's important is that this side is in between the two angles. So statement number 5 will be a conclusion. It's going to say, therefore, the triangle AED is congruent to the triangle BEC. Okay, and my reason here, well, this is the angle side angle congruence axiom. Okay, so other things we know in congruent triangles, this side would have to be equal in length to this side would have to be equal in length to this angle here would have to be equal in measure to that. Okay, looking at my last congruence proof, which is the right angle hypotenuse leg congruence theorem, or right angle hypotenuse side congruence theorem. And it says this: if the hypotenuse and the leg of a right triangle, so this only works for right triangles, are congruent to the hypotenuse and leg of another right triangle, then the triangles are congruent. So we're going to prove that these two triangles are congruent. And this is probably the most obvious. Again, I'm going to have my statement over there, my reason over here. I'm going to prove the triangles are congruent. Okay, I'm going to call the triangle, the first triangle, ABC. And if I call that triangle ABC, I should be calling, well, AB runs along the 8th side from this smaller angle to this right angle, so this should be called EDF. Statement number 1. Well, the first thing, the angle B is equal to the angle D, which is equal to 90 degrees. So that's given. So we know we're dealing with a right angle triangle. Statement 2. I'm going to say the hypotenuse here, AC, the distance from A to C, is equal to the distance from, well, I have to say E to F here. And that's equal to 10, you know, that's given as well. And statement number 3 is that AB, the side AB in that first triangle, the side running from A to B, that length, is equal to, well, I have to call this E to D. And we know that's 8. And again, that's given. I should be numbering my reasons as well. And note what we have is we've got the right angle in both triangles, we've got the hypotenuse in both triangles, and we have one of the other legs of the triangles equal. So statement 4 is therefore the triangle ABC is congruent to the triangle EDF. And my reason is my OR, H, L congruence axiom. Sometimes you'll see S for side there, so sometimes if you use an S for side you'll say RHS in there as well. Okay, so those are my 4 congruence proofs to prove triangles. Notice the 2-column proof is the most concise and effective. Do write in the full word statement, do write in the full word reason. I'm just putting S and R to keep the time down a little bit. I'm going to mention one last thing, which is this kind of notion, this CPCTC, which is an abbreviation for the phrase corresponding parts of congruent triangles are congruent. So I want to prove these 2 triangles are congruent, and hence I want to evaluate AE. A statement. Reason. 1. I'm noting that they're both right triangles, so I'll go for the RHL. So the angle A, notice there's only one angle happening at that vertex, so I can call that angle A. B has 4 angles happening, so if I was mentioning any of these angles, I'd have to include other points when I'm naming my angle. The measure of the angle A is equal to the measure of the angle C. Okay, and they're both 90 degrees. So let me put that in here. Is equal to the measure of the angle C, which is 90 degrees, and that's given. So we've shown they're both right triangles. The distance from A to B is equal to the distance from C to B, which is, well, actually I don't know what it is, that's just given. So we have a side there. Notice it actually doesn't tell me about the hypotenuse here, so I'm not going to use my right angle hypotenuse leg because I don't actually know about the hypotenuse. I'm going to actually rename that as just an angle. We have just a pair of matching angles there. So that angle is equal to that angle. This side is equal to this side. If I can show that this angle is equal to this angle, well then I have an angle-side angle congruence axiom. So I'm going to say statement 3. I have to call this, I'm going to call this angle ABE. The measure of the angle ABE, vertex at B, with legs going to A and E, and that's equal in measure to the angle BCD. And my reason there, well, that's again, it's the vertically opposite angles theorem. So we're using all our theorems to prove these things. Statement 4, therefore, the triangle ABE is congruent to, now I've said ABE, so I've gone from the right angle to the common vertex to E, so I have to say CBD here. Reason? Well, the reason is we have angle-side angle. It's the angle-side angle congruence axiom. We're asked to evaluate AE, so maybe I might just do that as a final statement. The distance from A to E, well, the distance from A to E, that part of this top triangle corresponds to this part in this bottom triangle. So the distance from A to E has to be equal to the distance from C to D, which is 3. And my reason there is because corresponding parts of congruent triangles are congruent. So, get used to that. You need to know how to prove triangles are congruent. You need to be able to draw a conclusion about corresponding parts. CPCTC, corresponding parts of congruent triangles are congruent. There are 4 proofs of congruence. Make sure you can use them all.